I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a few numericals based on a fringe width. Before doing the numericals, let us try to understand the concept of fringes and fringe width. So in which we are going to understand how fringes are formed, and this experiment is given by the scientist Young. So it is named after the scientist Young as Young's double slit experiment, because we are going to consider two slits here. We are calling it as Young's double slit experiment. So what do we have here is a source. This is a source S. We consider a monochromatic source. This is a monochromatic source. So what do we understand by monochromatic? Mono means single, chromatic means color. So light of single color, or it is single wavelength. So we are considering light of single wavelength. So the light that is coming from the source is emitted in all directions. So we consider the light that is falling on these slits. Now, these two slits are placed equidistant from S, means the distance it travels from S to this slit and from here to here is the same. Then what happens, because they are equidistant from here, these two sources will become coherent sources. They are coherent sources, means they are in phase. Since the distance travelled by the light from the source S to these two slits is the same, these two slits will act as coherent sources. Now, the distance between these two slits is considered as small d. Small d is the distance between the two slits. Now, the light that reaches this slit, as we have seen in Huygens principle, each point on this will act as a secondary source and sends out secondary wavelets. So these are the waves that are coming from the slit, first slit, and we also have waves coming from the second slit. These are the waves coming from the second slit. Now these waves coming from these two slits, when they superimpose on each other, depending upon how they arrive, if they travel the same distance, means if the path travelled by these waves is the same, then they arrive in phase. Means all those points will correspond to constructive interference, which gives rise to a bright fringe. So these waves will superimpose, and when they superimpose, if they are in phase, means crest falls on crest, or if a trough falls on a trough, all those points will correspond to constructive interference. So we have constructive interference. And whenever we have constructive interference, the point gives rise to a bright fringe. That is what we call it as bright fringe or bright band. This is a bright fringe or a bright band. Now, upon superimposition, if a crest falls on a trough, when you have a crest which falls on a trough, so it gives rise to destructive interference. We call it as destructive interference. And because of destructive interference, we will get a dark fringe or a dark band. So this is the background we need to understand. Also, we have the conditions which we have already discussed in the theory. When the path difference is an integral multiple of lambda, we have constructive interference. And when the path difference is an odd multiple of lambda, half multiple of lambda, then we get a destructive interference. So these two are conditions for constructive and destructive. So what we observe here is now the point at the center, because these waves travel equal distance, travel same path to reach the point here, they will arrive in phase. So the central fringe is always a bright fringe. So this, whatever you see in yellow, is the bright fringe. Now on either side of the bright fringe, in interference pattern, you will have dark fringes. So this is the dark one. This is a dark band. So this is a bright band or a bright fringe. This is a dark fringe. Okay. Now if you see, these bright fringes and dark fringes, they alternate each other. Means after dark, you have bright, dark, bright, and so on. Even on both the sides. If this is the central one, on either side of the bright fringe, you will have alternate dark and bright fringes. Now, if you have to number them, if m is equal to 0 is the central bright fringe, m is equal to +1, +2, because we are taking in the upward direction. M is equal to -1, -2, because we are going in the downward direction. And if you see for dark band, if this is m is equal to 0, this is +1, +2, this is -1 and -2 you will have. So what we are trying to observe here is, because of the superposition of waves that are coming from these two slits, what we see on the screen, this is the screen, which is placed at a distance of capital D from the two slits. So here, lambda is the wavelength of the light we are using. Small d is the distance between the two slits. And capital D is the distance between the slits and the screen. Now, because of this, we are having alternate bright and dark bands. And we are calling them as fringes. So what you are seeing here are fringes, alternate bright and dark fringes. In our interference patterns, the interesting thing here is all these bands are of equal width. If you see, this is the width of the bright band. This gives us the width of the dark band. This is for the bright, this is for the dark. If you see here in the diagram also, the width of these fringes is the same. Now we are going to see the expression for these fringe width, and we are going to do some numericals based on this fringe width. So fringe width or bandwidth is what? First, let us try to understand the definition. Distance between any two consecutive dark or bright bands is called the bandwidth or the fringe width. Because we have named the topic as fringe width, otherwise both mean the same. The distance between the n+1th and the nth order consecutive bright fringes from O is given by xn+1 minus xn. So xn+1 is the distance of the n+1th bright fringe from the central fringe, and xn is the distance of the nth bright fringe from the central fringe. So if we want to find the bandwidth, we do xn minus 1 minus xn. So we substitute in the formula and we get beta is equal to capital D by small d into lambda. So this is the formula we are going to use. Now let us have a quick recap of what we are going to use throughout our numericals. So we are doing numericals only on fringe width today. We may be taking the Young's double slit experiment or the bi-prism experiment, but we will calculate the fringe width. So fringe width is denoted by beta. And the wavelength Wavelength of the light source is denoted by lambda. Now, distance between the two slits. The two slits are placed or separated by a distance small d, and distance between slits and the screen. Slits and screen is capital D. So if we have to write the expression for beta, beta is equal to lambda d upon small d. Beta is the fringe width. How do we get the fringe width? Fringe width depends upon the wavelength. It depends upon the wavelength lambda. Capital D, which is the distance between the slits and the screen, and also small d, that is the distance between the two slits. So if the distance between the two slits increases, the bandwidth decreases. If the distance between the two slits decreases, the bandwidth increases. So what we need to understand? So beta is directly proportional to lambda. So if lambda increases, the bandwidth increases. And if d increases, then also the bandwidth increases. But if the distance between the slits increases, the bandwidth decreases. And the converse is also true. Means if lambda decreases, beta decreases. If capital D decreases, beta decreases. If small d decreases, the fringe width increases. That is what we are trying to understand. And now in our numericals, what we are going to do is, if you are given beta, the fringe width, capital D, the distance between the slit and the screen, and small d, distance between the two slits, we can easily calculate lambda from here. So lambda is equal to beta d upon capital D. So we'll use this formula directly from here. Or sometimes we may be asked to calculate capital D, at what distance the screen has to be placed in order to get fringes of so and so size. Then we'll use the formula capital D is equal to beta D upon lambda. Simple. Only from the main formula we are writing. So capital D is equal to beta D upon lambda. This is another formula. And sometimes we may be asked to calculate the distance or the separation between the two slits. So small d will be equal to lambda d upon beta. So upon doing these numericals, our concept of fringe width becomes very clear. Means we'll try to understand how wavelength or the distance between the slit and the screen or the separation between them plays a very important role in getting the interference pattern. Now coming to the first numerical. In Young's experiment, the distance between two images of the sources is 0.6 mm and the distance between the source and the screen is 1.5 meter. Given that the overall separation between 20 fringes on the screen is 3 centimeter, calculate the wavelength of light. It is a similar question, but only thing is the terms that we are using is different. Instead of directly giving it as the fringe width, they have given distance between two images of the sources on the screen. Means what? It is nothing but the fringe width. So let us write the data. So identifying the data is a very important thing while doing the numerical. So with the terms that are given, if you understand the theory behind it, you will be very easily able to understand the data. So distance between the images on the screen we call here as the fringe width 0.6 mm and the distance between the source and the screen, that is always capital D, 1.5 meter, and the overall separation between the fringes on the screen is 3 centimeter. So for 20, sorry here, we'll consider the distance between the two images of the sources as small d, and 20 fringes on the screen are at a distance of 3 centimeter. So 20 fringes in 3 centimeter. So what is the width of one fringe? 3 upon 20. So this will be 0.15 centimeter. 3 centimeter. So one fringe will be 3 by 20. That will be 0.15 centimeter, or we can write it in meters. 0.15 into 10 power minus 2 meter, or I can also write it as 1.5 into 10 power minus 3 meter, or 1.5 millimeter. Both are the same. Now we have to calculate the wavelength length. So again we'll write the formula. Beta is equal to lambda d by small d. So lambda is equal to beta d upon capital D. So beta we got as 0.15 into 10 power minus 2 into small d is 0.6 into 10 power minus 3 meter. Conversion from millimeter to meter. So this is into 10 power minus 3 upon capital D is 1.5. So what we are going to get is 0.06 into 10 power minus 5 meter. So we can shift the decimal place to 5 places and write it as 6000 into 10 power minus 10 meter, or it is 6000 angstrom. So the wavelength of light we are using here is 6000 angstrom. Now the seventh one, distance between two consecutive bright bands in the Young's experiment is 0.32 mm when red light of wavelength 6400 angstrom is used. By how much will this distance change if the light is substituted by blue light of wavelength 4800 angstrom? So when we are using 6400 angstrom, the fringe width is 0.32. Now, if this red light is replaced by blue light, whose wavelength is 4800, so what will be the change in fringe width? So we are going to understand this concept with the change in wavelength, how the fringe width is going to vary. So first let us write the data. We'll write lambda 1 for red light, 6400 angstrom, and beta 1, the fringe width in case of red light, beta 1 is 0.32 mm. Now, this is by how much this distance changes if it is replaced by blue light. Means we have to find beta 2 first and then find the change. Lambda 2 is equal to 4800 angstrom. Actually, what we have to find is the change beta 2 minus beta 1 or beta 1 minus beta 2, whichever is greater. We are going to find that. So what is the formula we have for fringe width? Beta is equal to lambda d by d. In the first case, beta 1 will be equal to lambda 1 into capital D by d. In the second case, that is with blue light, the fringe width beta 2 is equal to lambda 2 into d by d. I am not changing the values of capital D and small d because with the same setup they are telling. Means they are only going to change the source, that is the red light is replaced by blue light, and we are not going to change the other parameters, that is either the distance, capital D, or the separation between the slits. So they remain the same. Now how do we get? We'll take the ratio of beta 2 by beta 1. So it will be lambda 2 into D by D into D by lambda 1 into D. So D will get cancelled. So we have lambda 2 by lambda 1. So if we have to find beta 2, so beta 2 will be equal to lambda 2 by lambda 1 into beta 1. So this is the formula we are going to take forward now. Now let us see the units. 6400 angstrom. So this will be 6400 into 10 power minus 10 meter. This is 4800 angstrom. So 4800 into 10 power minus 10 meter. And this is 0.32 millimeter. So 0.32 into 10 power minus 3 meter. So that is the conversion. Now let us find beta 2. So beta 2 will be equal to 4800 into 10 power minus 10 divided by 6400 into 10 power minus 10 into beta 1 is 0.32 into 10 power minus 3. So this and this will get cancelled, and we have beta 2 will be equal to 0.24 into 10 power minus 3 meter, or this is 0.24 millimeter. 10 power minus 3 meter is 1 milli. So we have got beta 2 is equal to 0.24 millimeter. Now what they are asking, by how much will this distance change? Means how much will the fringe width change? Means we have to find beta 1 minus beta 2. Beta 1 is 0.32 mm and beta 2 is 0.24 mm. So 0.32 minus 0.24, it will be 0.08 mm. So it changes by 0.08 millimeter. Now another important numerical. Calculate the fringe width in the pattern produced in a biprism experiment, given that the wavelength of light employed is 6000 angstrom and the distance between the two sources is 1.2 millimeter and the distance between the source and the screen is 100 centimeter. What will be the change in fringe width if the entire apparatus is immersed in water whose refractive index is 4.3? Sorry, 4 by 3, not 4.3, 4 upon 3. Okay. So let us first write the data so that we'll understand what we have to do. Wavelength of light, lambda is 6000 angstrom. Distance between the two sources, that is small d, 1.2 millimeter. Distance from the source to the screen, 100 centimeter. What will be the change in fringe width? So definitely we may have to find the fringe width. Then find the change in fringe width. Okay, all the three are in different units, so we'll have to do the conversion. So this is 6000 into 10 power minus 10 meter. This is 1.2 millimeter. So 1.2 into 10 power minus 3 meter. 100 centimeter is simply 1 meter. And I will call this as beta 1. This is beta 1 in air because we are going to find the fringe width in water also. So for the fringe width in water, we'll consider it as beta 2. So what will be beta 1? Will be equal to lambda d by d. So 6000 into 10 power minus 10 into 1 upon 1.2 into 10 power minus 3. Okay, so this will be 0.5 millimeter. 0.5 into 10 power minus 3. So we got the fringe width as 0.5 millimeter. Now what we are given here, the entire system is kept in water whose refractive index is 4 upon 3. So when we write refractive index, how it is related to the wavelength is lambda 1 by lambda 2. That is 4 by 3. The refractive index mu is equal to lambda 1 by lambda 2. That is 4 upon 3. Now we'll try to get the relationship between the wavelength and the fringe width. Beta 1 by beta 2 will be equal to lambda 1 by lambda 2 because small d and capital D remain the same. We want to calculate B2, that is the new fringe width beta 2 will be equal to lambda 2 by lambda 1 into beta 1. So lambda 1 by lambda 2 is 4 by 3. So what will be lambda 2 by lambda 1? That will be 3 by 4. We can write it directly also, but it needs clarity. So 3 by 4 into 0.5. So this gives us 0.375 millimeter. Our beta 2 is now 0.375 millimeter. What they are asking is what is the change in fringe width? So to calculate the change in fringe width, we are going to take beta 2 minus beta 1. So beta 2 is 0. We'll take beta 1 minus beta 2, whichever is the higher value. So beta 1 minus beta 2, so 0.5 minus 0.375. So this will be 0.125 millimeter. So when the entire system is placed in water, the fringe width changes by, or I can say it is reducing by 0.125 millimeter. So thank you. For more numericals, you can refer to Engineering Physics by Gaur and Gupta or Cengage Publications, Engineering Physics by Cengage Publications. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.